Hello everybody, we're going to look at lesson 20. I have the actual assignment opened, and then if you go on Google Classroom, you can open up the slides, and you can also open up the periodic table, both of which will be useful. Remember, I said that I'd like you to have the periodic table printed off. I think that would be helpful for you. And up here, you should have a 1 written. You should have a 2 right here, and then you jump over to 13. And from 13 moving to the right, you have a 3, 4, 5, 6, 7, 8 written up on top. This would be extremely helpful for remembering how many valence electrons there are, which is going to be key for what we're doing today. So let's begin. So we're going to be looking at Lewis structures here. And in the last class, we brought up covalent bonding, which is what takes place when you share electrons. So an example of a covalent bond would be 2 chlorines. They both have 7 valence electrons, which means they each need 1 more electron. And so what they do is they can share an electron, so they both get a full shell. And since they have similar electronegativities, the electron goes right in between them. So an example, if you look at this, if you have a chlorine, and if you have another chlorine right here, let me make my screen bigger for you. So if you have a chlorine and then another chlorine right there, and this chlorine has 7 valence electrons, and then this chlorine has 7 valence electrons, then what they could do is they could just align themselves where that 7th valence electron that this chlorine has, we'll put it right here, and then the 7th electron from this one, we'll put it right here. So it would be like, that's where they each came from. So now, if you look at this chlorine, it would be like this chlorine has 8 valence electrons. Remember the octet rule. They all want 8 valence electrons. And then this chlorine right here has 8 valence electrons. You see that? So by sharing, even though they started out with 7, they each share, and now they both end up with 8. So what we do, the 2 electrons that they share, we call it the bonding pair. So the 2 electrons in the middle of both chlorines will be the bonding pair. And normally the bonding pair is found in between the nucleus of each atom. And what will happen is you have a region in the middle of them that will be negative because it has electrons. Remember, electrons are negative. So in this case, there's this region right here that's negative. And then what will happen is the center of the atom has a positive nucleus. And then the center of the atom right here has a positive nucleus. And it's positive because it's filled with positive protons. So I'll just make a bunch of positives in there. So it's got a bunch of positive protons in there. And so all these positive protons in the middle are attracted to this area of electrons right here because it's negative. And all these positive protons are attracted to the negative right there. So what it does is it forces this chlorine to want to go that way. This chlorine wants to go that way. And so it keeps them stuck together. We call that attraction right there the electrostatic force. So the electrostatic force is basically when you have the positive nucleus is attracted to the negative electrons that are in between each element. And then one thing, hydrogen, nitrogen, oxygen, and the halogens, which are fluorine, chlorine, bromine, and iodine. So HNO and the halogens. They are not stable in the presence of other elements. Basically, you can imagine these things, they're so reactive that they're not okay just sitting by themselves. So what happens, because they have such strong electron affinities, if you just, basically what I'm saying is if you dump a pile of hydrogen on the table, they don't just sit there by themselves waiting for something else to come along. They are so reactive that if there's a pile of them together, they will pair up. So in nature, you never find these things alone. You always find them in pairs, which is why we call them diatomic. So for hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, they will end up as H2, N2, O2. We call these diatomic. They're always coming in twos. Now, you can have, like hydrochloric acid, for example, is just HCl. It doesn't have to be H2Cl2 because the H and the chlorine are bonded together. So these can be alone if bonded to something else, but if all you have is just plain hydrogen, it'll be a bunch of H2s, never plain H's. So I'll be bringing these up later on, but remember, for these 7 elements, They are diatomic. They will always be found in pairs. That's going to be more important as we go on. Okay, so now what we got to do is we have to learn how to draw Lewis structures, and that is the main point of today's lesson. The whole thing I'm going to want you to do today is draw some Lewis structures and then attach the pictures of your drawings. And so just follow along as I go through these rules, and we will be doing Lewis structures. So what a Lewis structure is, it's a two-dimensional diagram that shows you where the covalent bonds are between atoms. And so it's easy to understand covalent bonds when you have a Lewis structure to look at. So what we're going to do, we're going to write the valence electron structure, and then we're going to move it around so that the unpaired electrons are in the middle of the two atoms. So remember, we had that valence electron structure where you have 1, 2, 3, 4, and you have a place where you put each dot. We did those a week ago. Now we're going to do those, but what we're going to do is we're going to draw them next to each other with the unpaired electrons in between the atoms. And then what we'll do, we'll draw them side by side where they can share the valence electrons. But then what we do is we draw a line to represent the electron pair. So let's do chlorine and chlorine. I'll do a Lewis structure. So I'll go through all the steps. So I just did this, but I'm going to do it and take a little longer so you see. So if you do normal chlorine, it'll be like this. And remember, we do element 1, element 2, and then 3, 4, 5, 6, 7. And then the next chlorine. Element 1, element 2, 3, 4, 5, 6, and 7. And then what we're going to do, we're going to take these unpaired electrons, and so for this next step, and let me say this, as you get used to these, you'll probably want to do this step every time. But as you do more and more of them, you'll eventually just skip straight to this step right here, which you'll notice I did it when I drew this a second ago. You're going to draw the two chlorines, and these unpaired electrons, instead of having them in the bottom, where electron 7 is supposed to go, have them facing each other. And then it's going to be like this. Also, I should refresh something for you. How do I know to draw 7 dots on chlorine? Well, I'm coming up with that by looking at the periodic table right here. And chlorine is right here. See chlorine right here. And it's in 7A, which has 7 valence electrons. All right, so let's continue this. So I have my 7 valence electrons, and then I'm going to finish it off. You just take basically what should be happening is we're going to draw one dot right here, so they share them. But in order to show that they're sharing 2 electrons, instead of drawing 2 dots, it's going to look like this. We draw a line between them. So that line represents the 2 dots that they're sharing. So what you'll get used to counting on this, when you see a line, that counts as 2 for chlorine on the right, but it also counts as 2 for chlorine on the left. So in total, this is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So that's what a Lewis structure looks like for diatomic chlorine. Let's do hydrogen, hydrogen. Remember, hydrogen, we look right here. Hydrogen is over here. It's only going to have 1. But remember, hydrogen is one of our weird exceptions. It doesn't want to get up to 8 valence electrons. Remember the first 4, hydrogen, helium, lithium, beryllium. They're okay with only 2 valence electrons. So let's go ahead and do hydrogen, hydrogen. All right, so we do hydrogen. We'll go 1, 2, oh, I'm sorry. Hydrogen is just going to have 1, and hydrogen is just going to have 1. And so then we redraw it with the dot facing each other. And then instead of drawing the 2 on top of each other, we can just draw a line. That's the Lewis structure for diatomic hydrogen. They share the 1 dot that hydrogen has is shared with the 1 dot that hydrogen has. It counts as 2 for both. And as we just discussed a second ago, Hydrogen is diatomic, meaning it is perfectly happy. I'm sorry, it's not. It is diatomic, but it's one of the exceptions where it's perfectly happy with just 2 valence electrons. All right, hydrogen. Now let's do hydrogen, and oxygen. So sometimes we're going to have more than one Lewis structure, more than one bond to draw. So multiple elements in our Lewis structure. So we have hydrogen, and we have oxygen, which will be 1, 2, 3, 4, 5, 6. How am I figuring out how many dots to draw? Well, for me, it's because I've done this a lot, so I just kind of remember. But what you'll want to do is look right here. Hydrogen, you'll remember, is only going to have 1 valence electron. Oxygen, O, all the way over here. You look up here, you see 6. It has 6 valence electrons. So that's how we know to draw 1 dot, and then 6 dots. So with this, what we're going to do, and I'll go over some tricks that'll help you when there's multiple elements like this. But you see, if I draw a bond between hydrogen and hydrogen, sure, they're happy, but oxygen's left out. You need to find a way to make all of them happy. So if I go like this and draw the oxygen, I'm going to start doing a trick you'll see as you do these. Whenever you draw, you can just connect the dots, like that little game you do on kids' menus. Some of you might have no clue what I'm talking about. Connect the dots was a little drawing game that used to be on kids' menus. So we're just going to connect the dots, and when you do that, draw a bold enough line that covers the dots so you don't have to redraw this over and over. So here's what I mean. Let's do a hydrogen right here, and let's connect these dots. Okay, so there's one of our lines. So remember, that counts as 2 for the hydrogen, and it counts as 2 for the oxygen. And then we can do this, connect these dots. And so that line counts as 2 for oxygen and 2 for hydrogen. So how many does hydrogen have? Well, the line represents 2. So hydrogen's happy. It only wanted 2. How many does that hydrogen have? 2. And let's look at oxygen. 1, 2, 3, 4, and then 5, 6, and then 7, 8. All right. So let me show you a double bond. This is going to be an oxygen bonding to an oxygen. So let's draw another oxygen on here. So let's draw the oxygen. 1, 2, 3, 4. And then if I draw my other oxygen right here, 1, 2, 3, 4. And then let's draw the unpaired electron. There's one there and one there. Remember, make them face each other. So here's one unpaired electron. Here's another unpaired. And then here's one of the unpaired. Here's another unpaired. So if you make a bond right there, are the oxygens happy? Well, let's count. 1, 2, 3, 4, 5, 6, 7. Let's do the other one. 1, 2, 3, 4, 5, 6, 7. They both have 7. They both want one more. So let's go ahead and do this. Now count it. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. They're both very happy. They both got the 8 that they wanted. Okay, and then let me do one more example, and then I'll go over some general rules when you're doing these. So now let's do 2 nitrogens bonding together. So let's look at the periodic table. You'll see nitrogen. You look up top, you'll see a 5. Let me get this out of your way real quick. So nitrogen has a 5 above it right there, you see? So let's go ahead and do diatomic nitrogen. So we have a nitrogen with a 5. So 1, 2, 3, 4, 5. Nitrogen with 1, 2, 3, 4, 5. So we have 1, 2, 3 electrons that need to be paired up with something. 1, 2, 3. So draw it like this with all 3 facing the other nitrogen. And you're going to do 1 bond and check how many you have now. 1, 2, 3, 4, 5, 6. Not enough. 1, 2, 3, 4, 5, 6, 7. Not enough. 1, 2, 3, 4, 5, 6, 7, 8. Now we're happy. So what you're going to start doing is you're going to have some large structures you're going to need to figure out, and it's really going to be like a bit of a puzzle. So here's some ground rules that you'll do. What you do is you don't need to think about this formula it has up there. I've been going over how to find the number of valence electrons. Hopefully you've printed off the table and written it on top. And so let me do H2CO, and I'm going to do this with you, and I'm going to follow some steps. And then after that, I want you to try to do the rest of the problems that are on there. I think what I'll do, if there's enough of you are struggling with this and you want to see some answers, I can post an image of the answers. I want you guys to try this and try it yourselves, and not just recopy what I do. That's why I'm not going to do every problem for you. But if you guys are struggling, you can email me, and I will be willing towards the end of the day to post like an answer key so you can compare what you did to what I do. All right, so H2CO. Let's do formaldehyde. So I'm going to write it up on top up here. H2CO. So step 1, write the electron dot symbol for every element in the compound. So you could look on the periodic table to see where I'm getting this stuff from. But we're going to do H, which only has one dot. H, which only has one dot. I'm doing two H's because notice it's H2. Carbon, which has 1, 2, 3, 4. And then oxygen, which is 1, 2, 3, 4, 5, and 6. So there's all of my, there's the 4 atoms that we'll be working with here. So that's step 1. You do the electron dot symbol for all of them. We're getting to where chemistry is really building on itself. Notice electron dot symbols were a very simple lesson from a week ago. Now they're a building block of what we're doing. So if you're falling behind, you don't know how to do an electron dot symbol, please email me. We need to get you caught up. Step 2, determine how many valence electrons are available. So what that means is how many, let me see if it says it clearer. So you're underneath, what I do is I'm going to write a number for how many times they're going to want to bond, meaning how many electrons aren't paired up with anything. So look at this. It's going to make one bond. Or think about it like this. This has 1, and what does it want to get to? Most of them want to get to 8, but remember, hydrogen's happy with 2. So this hydrogen wants one more bond. This hydrogen wants one more bond. How many bonds is carbon going to want? It has 4 electrons. It wants to get to 8. So it needs to make 4 more bonds. And then how many bonds does oxygen need to make? It's at 6 and wants to get to 8. So it needs to make 2 more bonds. And now we're going to place the element with the largest number of unpaired electrons in the middle. So the one that wants to make the most bonds, the one with the highest number out of what I've written up here, goes in the middle. And then we're going to put the rest of them around the atom. So I'm going to do step 3 and 4 at once. So which of these wants to make the most bonds? Well, that would be carbon. So let's put carbon in the middle, and let's put the rest of these things around the outside. All right. Now, create as many single bonds as possible by pairing up adjacent electrons. So let me draw on all my electrons. So carbon right here is going to have 4 electrons. Let's make sure at least one faces that hydrogen, one faces that hydrogen, and then we'll put the 2 more down here. I'm doing this because I know what's going to happen, but with these, you can make mistakes. I would suggest doing this in pencil. So if you end up realizing you drew an electron like on the top, you'd rather have it on the bottom, you can erase it and move it. Hydrogen only has one electron, so let's put 1 right there. Hydrogen has 1 electron, so let's put 1 right here. And then oxygen has 6 electrons. So it wants to make 2 bonds. So let's make 2 bonds face the carbon. And then it doesn't matter really where you put the other 4. So let's do a single bond with every single set of elements. And then make double bonds wherever necessary. So anywhere where they're not happy, make double bonds. And you'll notice carbon is not happy because if I count, remember, a line's count is 2. 1, 2, 3, 4, 5, 6, and that makes 7. So carbon's not happy. And oxygen, 1, 2, 3, 4, 5, 6, 7. So they both want 1 more. So there we go. Check the structure by counting the number of electrons and make sure it's equal to the value found in step 2. And then we know that we're done. So really, let's double check. Up here, we said hydrogen's going to want 1. Hydrogen has 1. Hydrogen's going to want 1. It has 1. Carbon's going to want 4. It has 1, 2, 3, 4 bonds. Oxygen's going to want 2. It has 2 bonds. So everything's happy. So that right there is the Lewis structure for H2CO. So what I want you guys to do is I want you guys now to go here. I want you to do these Lewis structures right here. Some of them I've already done for you. Do your best, do as many as you can, and then you'll take an image and you'll submit the image like you have in previous lessons. Please email me if you have questions, and if you've been trying it for a while and you're struggling and you'd like to see an answer key, or maybe if you just want to ask me like, hey, send me the image for these two problems. I've been working on, don't know what to do. If you need help, please email me and I'm willing to help you. Other than that, have a great day, and I will see you guys tomorrow.